in terms of movement of ions, absorption of ions into the body from the gut lumen, there's two routes. It's either transcellular, which means through the cell, and paracellular, which means, well, para means near, so it's between the cells. So let's have a look at that. So the movement of solutes, it can either be active transport across two membranes. What are the two membranes? Well, you've got the basolateral, the apical membrane of the enterocytes through the cell, transcellular, and then across the basal membrane, by active transport. And you've got passive movement via the tight junctions, which is paracellular. And we're going to be looking at three places. So in the small intestine is made up of three parts: duodenum, jejunum, ileum, and then you've got the large intestine, which is the colon. So we're going to be looking at the jejunum, the ileum, and the colon in terms of location. And then in terms of ions, we're going to be looking at sodium, potassium, chloride, and bicarbonate ions, looking at each of them in turn. First of all, looking at sodium absorption. How and where is sodium absorbed? Well, sodium is absorbed throughout the small intestine and large intestine. This is absorbed in the jejunum, ileum, and colon. However, jejunum is underlined here because it's mainly the jejunum, right? And how is it absorbed? Well, it's absorbed through four routes, okay? So the first route is sodium glucose or sodium amino acid co-transport. So what happens is, well, your body needs to absorb the glucose and the amino acids, doesn't it? So it can enter through a co-transporter for sodium glucose or sodium amino acids, right? The next route of sodium absorption is a sodium hydrogen exchanger. So the proton will leave the cell, sodium will enter the cell through this exchanger. Another route is parallel electroneutral sodium hydrogen and chloride bicarbonate exchanger. So it sounds a bit complicated, but I'll explain that. Well, essentially the sodium hydrogen exchanger happened at the same time as this, and the proton is coming from the water. The proton and bicarbonate coming from the water reacting with carbon dioxide, catalyzed by carbonic anhydrase, right? And the last route of sodium absorption is epithelial sodium channels. That's mainly in the colon. So looking at the first method of sodium absorption, well, sodium is absorbed along with glucose and amino acids by using energy from there's a transporter called sodium potassium ATPase. So let me explain this. Well, on the basolateral side, so here you've got the enterocyte, here you've got the lumen, and this is the basolateral domain. On the basolateral domain, there's a sodium potassium ATPase channel. What that does is it actively transports 3 sodium out and 2 potassium in from the basolateral side. And what this does is it causes a potential gradient, a sodium ion electrochemical gradient into the cell. So what this does is it provides the energy for glucose, galactose, and amino acid transport into the brush border, which is this, against the sodium glucose galactose gradient. So even though there's more glucose in here, it's still going to come in because the energy is being provided by this potassium ATPase channel, pushing the sodium out, causing sodium entry from this side and bringing glucose with it. And this happens, this sodium glucose and sodium amino acid co-transport through SGLT1 co-transporter, right? And where did the sugars and amino acids come from? Well, they come from the postprandial stroke, post meaning after, prandial meaning fed, so it's after you've eaten state that provides the sugars and amino acids which enter the enterocytes along with sodium, which is the first route of sodium absorption via the SGLT1 co-transporter. The next way that sodium is absorbed is through the use of a sodium hydrogen exchanger. So what happens is the sodium is transported in and the hydrogen is transported out. Now, why would you want to pump protons out into the intestines? Well, it's to neutralize the bicarbonate secreted by the pancreatic duct cells. So it's stimulated by the bicarbonate, and this causes sodium transport in, hydrogen transport out. Now, the way this happens is it's similar to the sodium glucose, sodium amino acid co-transport, in that again the sodium potassium ATPase pumps 3 sodium out on the basolateral side and 2 potassium in, right? Which sets up a sodium gradient, which then provides the energy for sodium to enter the cell and hydrogen to be pumped out through the sodium-hydrogen exchanger. And as I said, what stimulates this? Well, is the bicarbonate secretions as a result of, well, you've eaten. The pancreas has secreted bicarbonate. So the bicarbonate is causing a decreased lumen pH. If the decreased lumen pH, you want to balance that out by pumping hydrogen out through this sodium-hydrogen exchanger. And if there's too much proton in the cell, that's another reason for it to be pumped out. It's also stimulated by angiotensin, and the purpose of angiotensin is essentially to stimulate sodium and chloride absorption. So angiotensin stimulates absorption of ions into the body. So one point of comparison between this sodium-hydrogen exchanger and the sodium-glucose-sodium amino acid cotransporter is that they're both enhanced in the postprandial state. They both happen in the fed state. However, in the fasted state, sodium is absorbed in the ileum and colon, so not the jejunum, by parallel sodium-hydrogen and chloride bicarbonate exchange, which is inhibited by CAMP, CGMP, and calcium, not affected by pH or glucose. Let me explain all this, right? So in the fasted state, in the ileum and colon, similar mechanism, the sodium potassium ATPase on the basolateral side, that pumps 3 potassium out, 3 sodium out, 2 potassium in, which provides the concentration gradient, which allows the sodium-hydrogen exchanger to work, to pump the hydrogen out and the sodium in to absorb the sodium. Now let's think, where does hydrogen come from? Well, the hydrogen comes from this. Carbon dioxide and water react, catalyzed by carbonic anhydrase, to produce hydrogen as well as bicarbonate. The hydrogen is pumped out and the sodium is absorbed through the exchanger, but also, and this refers to the parallel part of it, the bicarbonate is pumped out and the chloride is pumped in through the chloride bicarbonate exchanger. So essentially what's pumped out? Well, proton is pumped out, bicarbonate is pumped out, so it's electroneutral. And what comes in? Well, sodium's come in and chloride's come in. So overall absorption of sodium and chloride, electroneutral sodium chloride absorption. And again, its absorption of sodium chloride is stimulated by angiotensin. Now one thing you'll simply have to memorize is that the absorption of sodium and chloride and pumping out of hydrogen and bicarbonate, therefore, is inhibited by 3 things. It's inhibited by calcium, it's inhibited by CGMP, and it's inhibited by CAMP. And CAMP is the main mechanism by which the absorption of sodium chloride is inhibited. And what can cause an increase in CAMP? Well, enterotoxins and Werner-Morrison syndrome, which I'm going to talk about in a second. So enterotoxins and Werner-Morrison syndrome cause an increase in CAMP, which inhibits the absorption of sodium chloride. If you inhibit the absorption of sodium chloride, then what's going to happen? Well, water is going to move into the lumen, causing diarrhea. So enterotoxins, as we know, cholera causes diarrhea. We can see the effects of that here. So the enterotoxins such as cholera elevates CAMP, inhibiting the sodium chloride absorption in the small intestine by parallel sodium hydrogen and chloride bicarbonate exchange. So water is going to remain in the lumen, causing diarrhea. And just as a summary, so enterotoxins cause diarrhea by elevating CAMP, which inhibits sodium chloride absorption.